In this video, I'm going to cover the third chapter from my book, which is about discrete time signals and the Fourier representation thereof. So we're going to look at how discrete signals are different from analog signals. We're going to look at sampling and interpolation of discrete time signals. We're going to look at the various ways of doing sampling and converting an analog signal into a digital signal, whereas some of these methods are zero-order hold, first-order hold, and Sinc interpolation. We're then going to look at the Shannon's theorem, aliasing of discrete signals, and then we're going to look at what the parameters of a digital signal are, which is its digital frequency and the particular case of what makes a discrete signal periodic. Then we're going to look at discrete complex exponentials, which are the basis of discrete time Fourier series, which we're going to discuss here. We're going to look at what it means to have a harmonics, so a discrete signal, and then what the series itself looks like. We're going to talk about power spectrum and then a matrix method of computing Fourier series coefficients. Okay, so in this chapter we're going to talk about the discrete time signals and their Fourier series representation. So this Discrete guy, he is a very important figure in this story, and you should learn a little bit more about him from Wikipedia. All right, so in the previous two chapters, I discussed Fourier series as applied to continuous time signals. And we saw that the Fourier series can be used to create a representation of any periodic signal. And this representation is made in chapter 1 using sine and cosine functions. And then in chapter 2, I showed how we can use the complex exponential to do exactly the same thing. And both forms are indeed equivalent. So in the previous two chapters, the discussion applied only to analog or continuous time signals. In this chapter, we're going to discuss Fourier series as applied to discrete time signals. Well, discrete time signals are quite a different thing than analog signals. And although there are some data which is naturally discrete, such as stock prices or number of students in a class, etc., but a majority of the electronic signals that we work with are sampled from analog signals. For example, music and any kind of measurement type signals. And discrete signals are generated from analog signals by a process called sampling. And it's also called A to D conversion. Okay. So what is a discrete signal? A discrete signal is continuous in amplitude, but is discrete in time. In other words, the amplitude can be anything, but the times at which the signal is measured is uniform in nature. For example, let's say every second we measure something. So the x-axis is uniform and discrete, and the y-axis is continuous or can be continuous. So discrete signal is often confused with the term digital signal, because the difference between discrete signal and digital signal is as follows. A discrete signal, as I said, is continuous in amplitude, whereas a digital signal, the amplitude is constrained. You know about binary signals, which are constrained to, say, +1 or -1 volts, or from 0 to 1 volt. So that would be a binary digital signal. And there are many other M-level signals. For example, a 16 QAM signal would have levels at ±1 and ±3. So that would be a 4-level signal. So when we constrain the amplitudes, we get a digital signal. Otherwise, the general term is a discrete signal. And and most of these discrete signals are described in terms of a sampling frequency, and what that means is how many samples there are per second. So here, for example, is a signal And let's say that this dashed line is an analog signal, and you can see that its amplitude varies all over the place. So this is a discrete signal, whereas the timing here is discrete, but the amplitude is whatever it is. This is a constrained digital binary signal. Here all the positive amplitudes have been converted to a +1 and all the negative to -1. So this is a fixed amplitude or constrained amplitude or a binary signal. So how do we generate discrete signals? Well, first of all, let me just go over the terminology that I use in my book. When I write x with these round parentheses, x of t, that stands for a continuous time signal. And when I have square brackets with an n in the middle, and that's a discrete time signal. So this right away gives us a clue that when we are talking about time for a CT or a continuous signal, it is referenced as t, and when we're talking about discrete time, we're talking about n, which is n is a sample number. So let me just go over how the sampling is done. And the way sampling is done is you pick a sampling function. Here I call a sampling function a p of t, and in this case we picked an impulse train, and it is the time between the two impulses for sampling purposes is the period of the sampled signal. So we just take these, multiply these two, and so we got this number here because that's the amplitude at that point right there, and this one is the amplitude at that point right there, and that's what you see here, and so on and so forth. So these dark points are this is the sample or the discrete time signal, and the sampler doesn't know anything about what's happening in between. For example, it does not know that the signal did not go from here to there, but in fact did this path. So it's possible that when we sample that we can miss some important detail, like in this case. So the ideal sampler is really an impulse train, as I just showed you, because it picks out the amplitude perfectly correctly. So now the idea is, if we've sampled a bunch of signals, how can we convert it back to the analog signal? And for that, in general, what I'm going to show you is that it's done in this way. We replace each sample with a shape. So here's some choices. This is a rectangular shape, this is a triangle, and this is the Sinc function. And there are many others, but these three basically fit the bill. They cover the gamut of what's out there. Okay, let me just go straight to the zero order hold. Okay, so zero order hold is a form of reconstruction, or it's also called sample and hold, where what we do is here's an analog signal, and that's the underlying signal. Of course, we don't know anything about it. All we see are these samples. So what we're going to do in zero order hold is we take each sample and replace it instead with this a rectangle. So here is a rectangle for that one. This one. This also, in a way, the name sample and hold is a very good one, because what it means is that the reconstruction process takes the sample and holds it for the period of the sampling frequency of the discrete signal. So here we're holding it here, and then we come down here and we hold it for that long, and then basically what we get is a stair-step function, and it's really not all that great looking, but of course, had we picked a much smaller sampling time, this would have looked pretty good. Now here's another way of doing it, and this is, we are going to replace each sample instead by a little triangle that twice the width, unlike the first one. This one is twice the width here, like this, and when we add all these things together, what we get is something like this, which is sort of a linear interpretation. This was a zero order hold. This is a linear connection between linear interpretation between these. When you add, for example, if you were to add these two, this is coming down, that's coming up, so this moves up here, and you basically get a straight line from here to there. That's what you've got. And this picture here is pretty decent looking. So this is what we call our first order hold, which is that it's the interpolation is linear. It's first order linear interpolation between the samples. Now there's one other one that's a very important one and used quite a bit, is called the Sinc interpolation. And the thing is that we ask ourselves, why would you want to use Sinc? It looks like such a complex signal. Well, the thing is, we use a zero order signal, and then we used a linear signal, and now we're going to use somewhat of an exponential signal, and that's what Sinc is supposed to represent. It has a lot of advantages, as we will see. Okay, so here, for example, is a signal, and it has these samples, and we want to recreate the analog signal. And the way we're going to do using the Sinc function is we replace each one of these with a Sinc function. Here, for example, are this one's here, that one's there, that one's there, that one's there. And we take all of these and we add them up. What we get is something like this. And of course, I don't give you the original signal, but this is a pretty good representation. And one of the nice things about it is that each Sinc function crosses 0 at the same time as all the others. So at the 0 point, they do not interfere with each other. In other words, at the point that this guy is maximum, none of the others, they're all 0 here. So they do not add to the actual amplitude for that signal. So this is a perfect reconstruction at that point, that and that and that. So it's a very decent way of doing reconstruction. So I mentioned the Sinc function, and it is a very, very important function. It is not only the most versatile, but also the most used piece of mathematical concept in signal processing. So I'm going to show you this function, what it looks like. It's basically sine of x over x, and it's 0. It's 1 at the center, and then it just kind of goes off, oscillating on both sides of it. Let's take a look at this picture. Now we can put the parameter of time, or the width of the main lobe, by changing the Sinc function in this fashion, just sticking a TS in here, and both in the top and the bottom. Okay, so assume, let's say that the TS is 1. If you put TS in 1, and we can use MATLAB to plot this thing, we would get this, and that 1 is here, and it's a minus 1, a plus 1, so the main lobe width is here. It's 2, or 2 times 2s. And then we take a look at where the zeros are, and the zeros are every TS. So it's 1, 2, 3, 4, so all the zeros alternating every 1 second. So this is a function in time domain. Now the same thing, if we did for TS equal to 2, if in this equation we put TS as 2, we would get this red figure. And now you see that the main lobe width is 4. It's minus 2 here, plus 2 here. And then this crosses zeros every 2 seconds. So here's 4, 6, 8, etc. on both sides. Now, one other way you will see the Sinc function plotted is by absolute values. So basically what we do is take this and flip it up, and flip it up, and same here, and same here, and now it looks like this. And it more often than not, you will see it plotted in this fashion, because it's kind of makes it easy to see where the zero crossings are. But otherwise, the main lobe looks exactly the same. And here's how you can plot it in MATLAB. Okay, now some of the useful and interesting properties that the sinc function has is that the sinc function has an area of 1. A normalized function, you add it up, you get area of 1. And the second interesting property is that as, let's go back to this picture, as TS, or this parameter TS decreases, gets smaller, we get the main loop keeps getting narrower and narrower. So imagine if ds were 0, you just get an impulse. So what it's telling us, basically, is that the sinc, the area under the sinc function is it becomes a sinc function actually approaches an impulse, like from this equation, and this is a very useful property. In fact, it tells us that if we add a whole bunch of harmonic exponential functions, we're going to get what is looking more and more like is an impulse train. And here's a sample of 90 of these added together, and they look pretty good. Okay, so what is sampling rate? I showed some pictures. Here's an analog signal, and it has been sampled. Here's some see the timing is uniform. We sampled it, and but we see that this peak has been missed. This one's been missed. This one's missed entirely. So looks like this one is not that great. Or we could do this one, and which is a bit faster. Again, the time between the samples is exactly the same. So this one looks pretty good because it has, captured most of the highs. So the question is, if this is too slow and this is probably maybe too fast, is there some other rate that's just exactly right? And the answer to that is that yes, there is, and there is an optimum sampling rate, and it's given by Shannon's theorem, and which is actually the same theorem is also credited to Harry Nyquist, who established the Nyquist rate and Nyquist threshold, Nyquist cutoff, etc. Different names for the same thing. And even before him, there were other people who had actually written papers and talked about the exact same idea. So although Shannon gets credit for it, he is not the first inventor. There were others before him. It's a very simple idea, but it's very, very important. And the theorem itself says, for any analog signal containing among its frequency content a maximum frequency of f max, right here. So let's say if you have a signal that says a spectrum like this, then this here is, it's hard for me to use this thing. Okay, so this is f max. Then the sampling rate must be greater than 2 times this. So the sampling rate must be greater than 2 times f max. Okay, I'll give that up. That's not working too well. So we can write it out like this: Fs is greater than or equal to 2 times f of max in the signal. And actually, even 2 times most often is not adequate. It needs to be more than 2 times fx, and 2 times the maximum rate. The number exactly at the threshold is called Nyquist rate, also Nyquist threshold, or even Nyquist frequency. They're all the same thing. So, okay, so now let me go back to the idea of what we said was the fundamental period of the signal. Now, fundamental period of the signal is its period, okay? So that it has something to do with the lowest frequency of the signal. So the fundamental period of the signal and the sampling period of the signal don't really have anything to do with each other. This guy is a function of the period of the signal, and this number, the sampling period based on the sampling frequency, which I said then must be more than 2 times the maximum frequency in the signal. They're independent quantities. One is a property of the signal, and the other is something external because we decide how fast to sample a signal. So TS, sampling time, we can change. But T0 is the property of the signal itself, and most likely cannot be changed. Okay. So now we'll talk about aliasing. What is aliasing? So what happens if we do not sample a signal at 2 times the maximum frequency? Well, what happens is we get something that's called aliasing. So this term aliasing applies strictly to improper sampling of an analog signal and coming up with this sample. So here, for example, are some samples that were collected, and now let's say that we're trying to compute a spectrum and maybe understand what kind of underlying signal from which these samples were collected. Well, here are some choices. So it looks like there's this frequency, there's that, there's so many signals these simple samples could have belonged to. Question is which signal, which frequency did they actually come from? This is a quandary. And this is a quandary of discrete signals, that when given samples we have really no way of knowing which actual signal they came from. I only show here 3 or 4, but in fact there's infinite number of waveforms that can fit these samples. So the way you figure out all the by the way, these frequencies are called aliases. So the lowest frequencies that through which these samples can fit is the you start from there, and then all the other frequencies would be called alias to that particular frequency. Here's a very simple equation that tells you how to compute alias frequencies, and I'll show you an example. So we'll take a signal that has we know that its frequency is 5 hertz, but we goofed up and we did not sample it properly. We should be sampling it at the rate of 10 hertz because that's what the Nyquist rate is. But let's say that instead we sampled it at 8 hertz, or only 8 samples per second. So in a situation like this, we're going to get aliasing. And we use this equation to compute where all the alias frequencies are lying. So you just stick m in here and compute right here. From here you compute what you get for this number. So what we get is, if m is 1, then we get 5 minus 1 times 8, or 3, and then we get 11, and then 19 hertz. So you see, even though the signal's frequency actually is 5, what we're getting is 3, 11, and 19. That's just not even close to what the actual signal is. So clearly the aliases are wrong. And pictorially, we can see how this works. So if we were to look at the spectrum of analog signals, here's what we should see: these 2 blue guys, right? The spectrum of a cosine or a sine is two pulses, one on each side of the origin at the frequency of the sinusoid. So here's 5, and there's minus 5. Related to not to minus 5 frequency, but minus, the index is minus 5 times fundamental frequency, which is 1, so that gives us minus 5 and a 5. So this is where they are. But what happens is that these guys repeat, and I'll talk about why they repeat later on. They repeat at the sampling frequency, which is 8 hertz. So take these blue guys, and then they repeat. You go to 8 hertz as the center, and here you place a copy, 2 green ones. And then you go 16, and here you place another copy of these red ones. Then you go 24, and here you place another copy, these orange ones. So now when we filter the signal, which is usually at half the sampling frequency, we only see this guy, and that's at 3. So we see this one at 3, or we can see this one at 11, or we can see this one at 19. That's what we calculated in this equation. And these are all alias frequencies. They're not, that is not what we had started out. We started out with the signal at 5 hertz and ended up getting a signal that's not even close to 5 hertz. So this is the effect of aliasing on the signal and its spectrum. So it's very important that signals be sampled correctly, at least 2 times, and oftentimes much more than that. When there's nonlinearities present, we need to sample a signal 4 or 8 times the maximum frequency. So if we do sample well and correctly, for example, here's a signal, and it has the highest frequency is 4 hertz, and the other frequencies are 1, 2, and 3 hertz. So if we were to sample this signal, I'm going to show 2 figures, one at 20 hertz and one at 10 hertz. And you'll see the effect of the sampling frequency on the spectrum of the signal. So just before I show that, let me just briefly talk about how to represent mathematically a discrete signal from an analog signal. So here's a analog signal. It's sorry, let's do this. And it has, it's written in a typical fashion, x of t, and all that with t's there. So this is analog. The discrete, in order to turn this into a discrete signal, sampled at whatever frequency, we would take t, because this is the continuous time, and we want to convert it into a discrete time. Discrete time is where t, remember we said we were going to name it by sample number n. So the discrete time become nts. So we change t to nts. And ts is same as the inverse of f of s. So we can write it 2 different ways. We can take t and we can change it to nts. I change nts here for all of the t's. Or we can write it as n over fs. So both of these are equivalent. All right, so now we take a look at our signal. And so this is let's take the signal, and we sample it at 20 samples per second. And when we do the spectrum, we see that so this is the spectrum, and we'll talk about why we are repeating copies, but the spectrums repeat, and they repeat at the sampling frequency. So the sampling frequencies were 20 samples. So every 20 samples, the spectrum repeats. And it's kind of nice that there's a little space, because we can filter it out, and we're not going to get much of this stuff. We're just going to capture the principal alias. This thing right here, the spectrum right in the middle, is called the principal alias. Now, if you were to take the same signal and sample it at 10 samples, or 10 samples per second, you see what happens. We get the same spectrum right here, but gosh, they're right next to each other. And if we wanted to filter them, we would get these other frequencies from the adjacent copies, and this would not be so great. So you can see that it's better to sample at as high as you can, above the factor of 2 times the maximum frequency. Okay. All right. Now we're going to look at discrete signal parameters and and how they differ from analog signals. Okay, so an analog signal is defined by the parameters of frequency and time. And discrete signals, obviously, we want to retain the same analogy. So for discrete signals, we use instead the letter n instead of the time. So the frequency, however, then gives us a problem, because in an analog signal, when we talk about frequency, we talk about certain number of degrees or radians per second, and time is in seconds. But here we're saying the time is a number, so, and it has units of sample instead of real time. And the frequency of a discrete signal then requires that it must be radians per sample instead of radians per time, as in the analog case. So the frequency of a discrete signal is indeed a very different type of frequency, and we give it a special name, and we'll call it digital frequency. And we'll use the symbol big omega to designate it. So an analog signal would be written like this. X of t is sine of 2 pi f0 of t. Here's t. But a discrete signal, the same frequency, would be written as nts. And I call ts is the intersymbol or intersample time. All right. So now what we can do is we have we can take ts, and remember I said that ts is the inverse of sampling frequency. So we can also write this particular expression, 3.18, as this one. X of n is sine of 2 pi f0, and here's n, but instead of ts, I've just put a fs on the denominator. So now we're going to define something called a digital frequency, this omega term, and that omega term encompasses all three of these. So here's 2 pi f of 0 divided by f of s. We're going to call that the digital frequency. So we can write this, the expression for a discrete sinusoid, as sine of discrete frequency times the discrete time parameter, which is n. So this is, of course, different than writing the equation for a analog signal such as this, which would be sine of omega t, except here sine of omega n. It's a little bit different. And the units here are this particular frequency is radians per time, and this is radians per sample. Okay, now the fundamental period of a discrete signal is defined as a certain number of samples instead of a certain time like we would do for an analog signal. And so to be considered periodic, a discrete signal must repeat after n0 samples. So that's sort of the definition of what a periodic discrete signal is. So in continuous domain, a period represents 2 pi radians. And of course, the discrete signal, we want to retain the same equivalence. So that means that in a discrete signal, also in n0 sample must cover 2 pi radians. So from that we can write this equation. The fundamental frequency of discrete signal times this fundamental period is equals to 2 pi. In other words, in n0 samples, the signal covers 2 pi radians. So here, for example, we'll take a look at a signal, a discrete signal. This is the analog version, and we see that the period in time is 1 second, and because it repeats from here to here, 1 second. Now, in same thing, we have a sample version of the same thing, and this thing has been sampled at looks like 9 samples, and so the period of this discrete signal would be called 9 samples. Now, one other way we can write it is in terms of the phase. So in these 9 samples, it has covered 2 pi. So each one of these ticks, then that means that every time n changes, it covers pi over 4 radians, and you add those together, and it goes from minus pi to plus pi in this time period. So it's the same for this and for the analog and the discrete signal. Okay. Now we look at the periodicity of discrete signals, because we're talking about Fourier series, so we're talking about periods of things. And here's x of t would be defined as is periodic if we can find some t0 that when the signal has moved t plus t0, and we get the same signal back. Same thing with discrete signal. If there's a certain number of samples that have been traversed and we get the same signal back, then that discrete signal is periodic. Now, we'll take a look at, in sinusoids, since we're using sinusoids as basis functions for Fourier series, what the same thing means. So for a discrete sinusoid, we would say omega 0 times n should be equal to cosine of omega 0, n plus n0. So this is sort of the condition of periodicness for a discrete signal. And now we can expand this like this, simple trigonometric identity. And we open this up, then that means that this term here is equal to this and this and this, right? We just plug these values in. And we find that for this cosine to be periodic, for this guy to be equal to this guy, these terms must be 1 and 0, because then that's what we have left. This is all 0, and then only thing left is cosine 0. And so for these two conditions to be true, what we need is omega 0 times n0 needs to be an integer multiple of 2 pi, or the discrete, or we call the fundamental discrete frequency divided by 2 pi should be equal to an integer divided by n0. So this is the condition for a discrete sinusoid to be periodic. That is, it is periodic if and only if its digital frequency is a rational multiple of 2 pi based on the smallest period of n. And we'll take a look at some examples of under which conditions these sinusoids are periodic. So we can write an expression for the fundamental period of a discrete periodic signal as 2 pi k divided by omega 0. Alternately, we can write omega 0 as 2 pi k divided by n0, same thing. So let's take this signal. This is a discrete signal. The dashed lines are here just to kind of give you an idea what it is. So here's my discrete signal, and I'm asking you if this is periodic signal. Well, actually, if you look at this form, the cosine right here, cosine omega 0 n. So anything that comes before the n must be omega 0. So clearly in this case, 2 pi over 5 is the digital frequency of this signal. So the digital frequency of this signal is this number, because that is the coefficient of the time index n. Now the fundamental period, you also see that this term is equal to 2 pi k over n0. And the smallest k we can use is 1. That means n0 is 5. So n0 is 5. That means that we have 5 samples before the signal repeats, and that is indeed the case here. Sample 1, 2, 3, 4, 5, and then the signal repeats again. Or you can apply that equation, which is 2 pi over omega 0. And I said omega 0 is 2 pi over 5. Divide all that, we get 5. So the answer is yes, this discrete signal is indeed periodic. And the effective phase? None. Okay, so we want to look at another example. What's the period of this discrete signal? Well, once again, we see that this right here is the fundamental frequency of this discrete signal. And so what we do is we try to compute n0, but we find that we don't get an integer unless k is 3. That means that it takes 8 samples for this signal to repeat. It does not repeat in one period of sine as you would think. So in this case, the period is 8 samples, and it takes more than 2 pi to get to that. In fact, it takes 6 pi to get to a point where the signal repeats. Okay, now here's another signal. This is a discrete signal, and we want to know if it's periodic. So we say yes, the digital frequency of the signal is 1/2. So its period from the equation that I showed you, 2 pi k over omega 0, comes out to be 4 pi k. Now, problem is that the n needs to be an integer, and there is no k that can make this number an integer. So that tells us that this particular signal right here, this one, even though it's discrete, even though it's a sinusoid, it's still not periodic in a discrete sense. Hence, it'll never be periodic. All right, so now we use discrete complex exponentials as basis for DT Fourier series before, and we're going to continue on that because that is the most typical way that Fourier series is represented. All right, so let's take a look at how we would write a complex coefficient for a continuous case and for a discrete case. So in a continuous case, we write e to the j omega 0 t, and remember we replace t with n, and now we would write it as t j. This is the discrete frequency omega 0 n. So this is the discrete form, and this is the continuous form. We're not going to be dealing with continuous forms anymore because in this section we're talking only about discrete signals. So now we say we can write this particular complex exponential in this form where we show the period of the signal and sample. So writing this and this is exactly the same. And what we're going to be talking about are the harmonics of this discrete fundamental complex exponential. And things kind of get complicated and tricky. Okay, the range of the digital frequency is 2 pi. So to obtain its harmonic, we increment its frequency by adding an integer multiple of 2 pi to the digital frequency, and not by multiplying it by an integer. We wouldn't say it's 2 pi, 3 pi, 4 pi, etc., as we do for analog harmonics. So the frequency of a kth harmonic of a discrete signal would be omega 0 plus 2 pi k. So if you have omega 0 as pi over 4, then its next harmonic would be 11 pi over 5, which is obviously not 1 or 2 times pi over 5. So the second harmonic is pi over of this is 11 pi over 5. So this is kind of an important point. The analog and discrete harmonics have slightly different definitions for the purposes of the Fourier analysis. So let's take a look at it again. Discrete fundamental would be specified in this fashion as 2 pi over n. That's the digital frequency. And its harmonic would be that plus 2 pi k times n. Now, where we find something very interesting by defining the harmonics in this fashion, and that is that each of these harmonics defined in this fashion are exactly the same. So where each and every harmonic of an analog signal looks very different, you can see its frequency is increasing. It shows more ups and downs, etc. The discrete harmonics is defined by adding 2 pi, integer number 2 pi k's. For each k are not distinct from each other at all. They're in fact all very identical, and you can see why from this proof. You take 2 pi n, you add 2 pi k, then you break this thing out because they're just powers. This part here, as I showed you in lecture 2, is 1. It's comes out to be 1. And all you're left is this, which is the original harmonic. So what that's telling you is, ignore this part, put the n here, and you've got the original one. So what that's telling you is that the harmonic, all harmonics obtained in this fashion are identical. All right. right, so I show a little example in my book here. We start out with a signal of fundamental frequency of pi over 6, and we plot two of its harmonics against it using the procedure that I just showed you, and they are all identical. So this example demonstrates that for a discrete signal, the concept of harmonic frequencies does not lead to any meaningful harmonics. They're all identical. All harmonics are the same. Then, how can we do Fourier analysis on this signal if it has no distinct harmonics, if all basis signals are identical? So the trick is that in defining the discrete harmonics, we only looked at discrete signals that differ by a phase of 2 pi. Remember I said we kept incrementing it by 2 pi. So although the harmonics obtained this way are harmonic in a mathematical sense, or in fact they're identical, they're pretty much useless in a practical sense because they're not distinct. So the question is, what do we use for harmonics in discrete Fourier analysis? Well, the secret hiding place for the discrete harmonics is inside the 2 pi range. Not every integer multiple of 2 pi, but inside the 2 pi range. And there are only n unique harmonics. And recall I said n is the period of the periodic discrete signal. So if it's 10 samples long, then there's only 10 harmonics. Whereas you recall in analog signals, the number of harmonics can be infinite. So we would define these n harmonic frequencies like this. So you take the digital frequency and then you multiply it by k. So we'll take a look at an example. And we find that any k that's more than n minus 1, 0 to n minus 1, we'll just repeat this. We'll get exactly the same thing. And let me show you an example. Okay, so here's a signal that has a discrete harmonic frequency of 2 pi over 6. So we are going to see that it has, the period is 6, so we would be incrementing. So the first one is 2 pi over 6. Second one is 1 times that, 2 is 2 times that, 3 times that, 4 times that, 5 times that. This one is 0, so this is 0. And after that, we go right back. Next harmonic becomes identical to the 0th harmonic, and the 7th one is same as 1. So we only need n harmonics. And so let's go to the example. Okay. So here's a signal which has the same signal, which has a fundamental frequency of pi over 6. So our first harmonics, when you multiply it by 0, is, as you see, it's a cosine, and we could just get flat line. Now, our analog frequency, fundamental frequency would be 0, or the 0th frequency. Now, for the next harmonic, we would, in this case, we would multiply f0 by 1, and you can see here's the analog fundamental. The discrete fundamental, however, is 0 plus 2 pi over 6, or pi over 3. And we get these samples. This is for the real and the imaginary part. Now, for the second harmonic, k is 2, so it's twice the frequency of the first one, and we can see it's oscillating. The harmonic, the discrete harmonic, however, is pi over 3 plus 2 pi over 6, or we get 2 pi over 3. That's the next frequency, and you can see that it's the number of samples is different. Now, this is the third harmonic. Once again, it's incremented by 2 times pi over 3. This is pi over 3 actually. So this is 0 times, this is 1 times, this is 2 times, This is 3 times. When you do 3, the 3's cancel, you just get a pi. This is 4 times, and this is 5 times. So the original frequency plus each time we add k times pi over 3 to it to get the new frequency. And we can see that there's, by the time we get to number 6, we have gotten exactly this case back. But if you look at the analog case, all the frequencies look different. Whereas if you look at the discrete, after number 6, we get the same pattern all over again. So what that tells us that discrete harmonics, there's only n of them. N is the number of samples in the period for the discrete signal. So in a way, it makes the job easier. Because we only have to compute rather than only n harmonic coefficients to compute rather than an infinite number as we would for a discrete case. This is a little bit of a confusing part, but remember that the period is the important point here, and then and that there are only n useful harmonics that we can use. So a discrete time Fourier series is a discrete representation of a discrete time periodic signal by a linear weighted combination of these k0 distinct complex exponential. And k0 is really just the same as n0, which is the number of samples in the period. So we would write the equation for the synthesis this way, and the expression for the coefficients in this fashion. And remember that we only need to do n0 calculations. Any more than that, they just repeat and don't really give us anything. So the GTFS coefficients for the kth harmonic are exactly the same as the coefficients of an harmonic that is an integer multiple of n0 samples. So, okay, we're going to look at some examples. So let's take a look at this signal. We want to find its discrete time Fourier series coefficients. The fundamental period of this signal is 10 samples. That we know because this right here is the digital frequency, and the denominator is n. So hence this equation will have at most just 10 coefficients. So we can write this signal in complex exponential form. Here it is. It's just a sign, so it's 1 over 2j positive exponential minus 1 over 2j negative exponential. Note that because the signal has 3 components corresponding to index k of -1, and which is this one, and 0 and 1, we can actually write the answer by just observation. And then we know that even though there are 10 possible harmonics, their coefficients are 0. So we can actually so here are these coefficients. The 0 is 1. Here's 1 for the 0th, and for plus and -1, the coefficients are 1/2. So that's what these two numbers are. Now, the thing about which I said earlier is that as you increase k, you keep recomputing. These coefficients will keep reappearing every 10 samples. In other words, the coefficients repeat at every n0 or at every sampling frequency, and that's what we're seeing here. And so we started. This is our time domain signal, and this is the signal that this one or that was, these two are same. And that's what this is the time domain signal. This is what we begin to call the principal alias. This is the result of the first frequency, and these are really it's DFT's way of I'm sorry, you shouldn't call it DFT. It's still discrete Fourier series. Is that it's trying to tell you that it doesn't really know which the correct frequency is, and is telling you that it could be any of these frequencies. So that the frequency ambiguity, that concept, leads to replicating spectrums, which you will see for all discrete time signals. So anyway, we could go and compute all these things, and we would find that we would, that was something that we did by observation. We could, spend a lot of time in doing all this and come up with the same thing. Okay, so here's another one. We are going to want to compute discrete time Fourier series coefficients for this signal. It's a discrete signal. It has a DC component, then there's this cosine and a sine. And now what we have is a cosine, which is 5 samples. We can see here it's the period is 5 sample. Sine this sine has 4 samples. So for this composite period, the whole signal repeats with 20 samples, because that is the least common multiple of 4 and 5. So this signal repeats every 20 samples. And hence the fundamental frequency of this signal is 2 pi over 20, or pi over 10. So here we plot the samples, and now we're going to compute the Fourier series coefficients, which again we can do if we write it in exponential format. We can just write by observation. Here I've computed the 0th coefficient, and that is this number, and it turns out that there's 2 others which fall here. And then here's the principal alias, and then this principal alias will repeat every 20 samples, which is the period or the sampling frequency of the signal that we calculated up here. So you can see it repeating. So this thing repeats every 20 samples. And again, that is because of the frequency issue with discrete signals, because of the aliasing issue. Okay. Okay, so here we are going to compute the dTFSC of a periodic discrete signal that repeats with period 4 and has 2 impulses of amplitude 2 and 1, as in this figure. Let's go see. This is a pretty simple looking time domain signal. We can write it out in this fashion using the coefficient equation, and the spectrum we get is like this. And once again, if you plot it here, you see that it's repeating. It's repeating every 4 samples, which is the period of this signal, 1, 2, 3, 4. And these are computed fairly straightforward in this fashion, or you can use MATLAB. So here's another signal. It's in time domain. It looks like this, like this, like this. It's repeating. Now, when we compute the discrete Fourier series coefficients for this signal, we use our dTFSC equation. Let's go down here. This equation, and then we can plug all these values in, and from here we can compute all these values, and plotted they look like this. This is the principal alias, and these are the repeating aliases. Okay, now the most important signal is a square pulse signal. It's of a width L samples and has a period of n, and we would draw it something like this. Like this. And we find that we can use the same method to compute its coefficients. There's a bit of mathematical manipulation required to compute these things, but it's not too difficult. We actually will use this expression, the series summation equation, and when you use that, you come up with a very nice looking expression, very similar to the analog expression that we calculated, and that is that the coefficients are function of this thing, and this function here, it looks surprising like a sinc function, but it is not the sinc function. It is something called Dirichlet function or Dirichlet function. And whereas the sinc function was sine x over x, this is sine over a parameter divided by a slightly different parameter. So this thing is a Dirichlet function. It's very similar to the sinc function, except it repeats. The sinc function does not repeat, but Dirichlet function repeats. And when we have discrete signals, we get the spectrums for this particular function repeats, as you can see. So this is basically a sinc function that's repeating. And the function itself is called Dirichlet. In MATLAB, you can compute it using this term called Dirichlet. Okay. Now we can take a look at the discrete time Fourier series coefficients of a discrete pulse. So here, pulse width is huge. In fact, it's equal to all the samples, and we here the pulse width is starting to so here's 1, here's 2, and we show the coefficients plotted like this. The coefficients here are all 1. Here they begin to make an appearance, and as the width gets narrow, you can begin to see the Dirichlet, which is really the sinc function, but anything beyond the second lobe has been damped out. And this is a pulse width of 5. In fact, actually, the number of lobes we are seeing is 1 less than the number. So here we would see 2, so that would be 1 lobe, there's 2. And 5 would see 4, so 1, 2, 3, 4. 1, 2, 3, 4, yes, and then 1, 2, 3, 4. And same thing with 7 and 9. So what that tells you is that as the pulse is getting narrower, as the pulse width is getting wider, we're starting to approach an impulse train. And this is for a discrete signal, whereas in analog signal you get almost exactly the same thing, except it's not discrete. Okay, the power spectrum is calculated using exactly the same thing as Parseval's theorem that I said, except in this case we square either the time domain samples or each of the frequency domain coefficients that we calculated. So both give us the power spectrum for the signal. So we take CKs and we square them, and we have got the power spectrum. So now there's an alternate method of, you saw that computing the discrete time Fourier series coefficients looks pretty difficult, something that you would do for homework in school, and not, certainly not something that's used in the industry, where a matrix method is used for computing these coefficients. And to do that, we define something called a twiddle factor, and you can see that we define it this way, and if we know the period of the signal, this number more or less becomes a constant, and then the DFS and the inverse DFS equations are given this way, except they have powers of n, k, so we can we know n and k because once we know n, we know that this is a maximum number for little n is n, and maximum number for k is also n. So it kind of defines the universe of values we have to compute for this term to the power of nk, and that's what this is. So we can actually compute these and keep them in a table, and then when we are asked to compute the coefficient, all we do is pull out this matrix, which has already been pre-computed for a certain size, say 4 by 4, multiply it by xn and divide by n0, and we've got the coefficient. So this is a matrix method of computing discrete time Fourier series coefficients, and is actually pretty much the same thing that's used in DFT and subsequently in FFT. So let me just briefly go over the summary from this chapter. We talked about discrete signals, digital signals, what is Nyquist rate, what is a digital frequency, what is aliasing, and discrete time Fourier series coefficients. So an ideal discrete signal is generated by sampling a continuous signal with an impulse train of desired sampling frequency. The time between the impulses is called the sample time, and the inverse is called the sampling frequency. Sampling frequency of an analog signal should be greater than 2 times the highest frequency in the signal. The fundamental period of a discrete periodic signal given by n0 must be an integer number of samples for the signal to be periodic in a discrete sense. The fundamental frequency or digital frequency of a discrete signal is given by 2 pi over n0. Period of the digital frequency is defined as any integer multiple of 2 pi. Harmonic discrete frequencies that vary by integer multiple of 2 pi, such as 2 pi k, etc., are identical. We increment digital frequency by itself, or 2 pi over n0, and use the n0 sub-frequencies as the basis set for discrete Fourier analysis. These are harmonic and they're distinct. There are only k0 harmonics, k0 is same as n0, are present only instead of an infinite number as in analog analysis. Beyond the 2 pi range of harmonic frequencies, the discrete time Fourier series coefficients repeat because the harmonics themselves are identical. In contrast, the CT signal coefficients are aperiodic and do not repeat. This is because all harmonics for a continuous signal are unique. And here's the expressions. The coefficients of a discrete periodic signal are discrete, just as they are for continuous time signals. The coefficients around the zero frequency are called the principal fundamental alias or principal alias or principal spectrum. The spectrum of a discrete periodic signal repeats with sampling frequency of FS. This is something new, and we did not talk about it in case of analog signals. Sometimes DTFSC coefficients can be solved using closed form solutions, but in majority of the cases you need to use matrix methods. And matrix methods are fairly easy to set up, but if the size gets large, they can become computationally intensive. So we use fast matrix methods, and which are the basis of methods called FFT, which we'll talk about later. And that is the end of this lecture. Thank you.